Okay, so we've talked about orbitals and shells and subshells, and now I'm going to talk about how we actually determine an electron configuration or an electron arrangement. So electron configuration is the description of which orbitals in an atom or ion are actually occupied by electrons, and how many electrons are where. Now, it's important to know that for every atom, the orbitals are the same, right? Which orbitals appear and in which order, they're always the same. So what I gave you is just a broad, or what I'm going to give you is just a outline for every atom. Only thing that's left to do is just fill in however many electrons we have available to us, right? So what's really going to make the electron configuration of hydrogen different from helium is that hydrogen, and this is neutral hydrogen, how many electrons does neutral hydrogen have? Hopefully you said 1, right? Because if we look on the periodic table, its atomic number is 1, meaning it has 1 proton and therefore 1 electron. Helium has 2 electrons. Carbon has 6 electrons. And these are all for the neutral atoms. And fluorine has 9 electrons, right? So that's all that really is going to happen. We're just going to fill in the appropriate number for ever many electrons we have, right? So here's how we determine electron configuration. The orbitals are always going to fill in increasing energy, right? Electrons are lazy. Electrons, if nothing else, are very, very lazy. So they're going to fill in order. Now, the order is this. And for now, you don't have to worry about memorizing it. I'm actually going to show you how you can figure out the order of these without having to worry about anything. For right now, it's very simple. 1s, right? We go up in shells. First shell, 1, 2, 3. 1s. And then within a shell, second shell, there's 2, right? Second shell, there's 2 subshells, 2s and 2p. And within the third, there's 3s, 3p, and 3d, right? So we'll go, in every s, there's 1 electron, or not 1 electron, 1 orbital. In p's, there's 3, and in d's, there's 5. And now what I'm going to do is I'm going to fill them in. Now, the other thing you have to know is that each orbital can hold up to 2 electrons with spins paired. Oh, I mean for that to happen. By the way, ignore this order for now. So things get a little more complicated. I'll explain why in a bit, and I'll show you how to just know that. So we have to show them spins paired, and when there's a set of orbitals of equal energy, it becomes half filled before it becomes completely filled. I'll show you that by going through. So here's how it works. Let's say we start with just hydrogen, very simply. Start with hydrogen. How many electrons does hydrogen have? Has only 1 electron, right? So if I want to show that electron configuration of hydrogen, I'm going to draw an arrow in here like this. And I'm going to draw the arrow up. If it's by itself, I just draw the arrow up like that. Okay? Does that make sense? That's to show the spin. So we draw arrows either up or down to show the spin. And I could have just as well written it down. It doesn't matter because we don't really care what spin an electron has by itself, right? Now, if I go on to helium, right, what I'm going to have with helium is I'm going to have 2 electrons. And I'm going to go 1, 2, right? So I have to show them opposite spin. I have to show them paired. Okay, so let's do the next one. When I get to lithium, right, I have 3 electrons. 1, 2. This orbital is full. The 1s orbital is full. Now I have to go up to the next one. So electrons are lazy. They want to be in the lowest energy they can, or at least we're describing their ground state. They want to be the lowest energy they possibly can. They're only going to go up to a higher energy when you force them to, when there's no room here. So there's no more room. This third one has to go up here, like that, right? So let's continue on. And I'll erase this. 1, 2, and I'll go up to 2p. All right, so if I have boron, 5 electrons, I'd go 1, 2, 3, 4, 5. That's easy, right? Now let's consider carbon. Carbon has 6 electrons. Now something interesting happens with carbon, right? I've got 1, 2, 3, 4, 5. And you can kind of see as I move across the periodic table, each new electron just goes to the next space. So what's going to happen is this, we can either put the next electron here in this orbital or over here. Now, the analogy I like to use here is sitting on a bus. Let's say you go onto a bus and there's those double seats, right? Like the double seats. And this one's occupied and that one's occupied. Where are you going to sit? Are you going to sit here or here? Or are you going to go sit over here where you can sprawl out and put your book bag everywhere? Most people are going to pick this. Electrons are lazy and they're selfish. They want an orbital by themselves if they can. And the more scientific explanation is that there's energy. It requires energy to pair up. So the lowest energy possibility is for them to be unpaired, is to be over here in its own orbital. So as long as the orbitals are degenerate, as long as they're the same energy, the electron doesn't have to go up any other flight of stairs to get up to this orbital. So it just goes over here. It's the same energy. So the 6th electron actually goes here, right? So we continue in that way. If we do nitrogen, which has 7, the 7th electron would go here. And oxygen, which has 8 electrons, its next electron now begins to pair up. So we pair up like this. And we just continue up the scale like that until we run out of electrons. So we just continue up in higher and higher energies until we don't have any more electrons to add. So, fill in order. You can use this order for now, and I'll actually explain this, just give me a second. Each orbital can hold up to 2 with spins paired, so we draw them paired. And then when you have a set of orbitals of equal energy that are degenerate, each orbital becomes half filled before any of them become completely filled. So you do, and that's the case, that's what I'm referring to when you have 3 orbitals. You go 1, 2, 3, and then you pair up. So, this weird order. So what's actually happening here, the reason for this is you have, 1s. Then you have the second shell, 2s. Actually, maybe a better way I can say it is, imagine that here is the difference in the energies of the orbitals. So, 1s is here. And I'm just going to draw the s's for now, kind of show the lowest energy of the draw this a little bit better. I'm going to draw them here. Right? So the idea is these are some energy apart, right? That is set out. Now, in the second shell, right, we have a 2p as well. In the third shell, we have 3p, but we also have 3d. And what happens is when you get that many subshells, the energy increase from each subshell actually begins to collide with the next shell. So what happens is 3D is actually a little bit, not very much, but slightly higher in energy than 4s. So electrons being lazy are actually going to go into 4s before they go into 3D. Now, as I said, I don't want you to memorize any ridiculous, don't worry about trying to shove any mnemonic in your head that tells you the order of the electrons. I'm going to teach you how to know the order of these subshells by looking at the periodic table, and there won't be any confusion for you there. So, but for now, you can refer back to this: 1s, 2s, 2p, 3s, 3p, and then it's 4s, and then it gets all kind of garbled from here, right? So the 5s comes before the 4d, and then the 4f comes way up here, so they get all kind of garbled and messed up. But we'll talk about those a little bit later. So, drawing that box can really be a problem like drawing that box diagram takes up a lot of space and takes time, and it's really obnoxious to draw every single time. So we actually have a shorthand notation for showing electron configuration. So let's go back to just, let's do carbon again. So 6 electrons, right? When I did the diagram, 1, 2, 3, 4, 5, 6. What I'm going to do is I'm actually going to list out all of the subshells. I'm not going to, I'm going to list out the subshells. So I'm going to list out 1s, 2s, 2p. Now I'm only going to list out the subshells that actually have electrons in them. It's important to understand that, 3s is up here, just is empty, right? But what I'm going to put a subscript after each one that tells me how many electrons are in the subshell. Not in an orbital, just in the subshell. So s has 2, p also has 2, right? Even though they're in different orbitals, there's 2 in the subshell, right? In the whole subshell. The electron configuration for oxygen would just have 2 more. 8 electrons. It would have 1, 2, and it would be 1s2, 2s2, 2p4, right? Because there'd be 4 electrons in that 2s, and the 2p, right? So in the 2p, there'd be 4 electrons. 1, 2, 3, 4, and there's 4, right? So, as you're going up in this order, right, you're just going to end up going always in this same order here, filling up each subshell. So S's cap out at how many electrons, right? S's only have 1 orbital, so the maximum number you're going to see as a subscript above an S is 2, right? Then they're full. P's have 3 orbitals, so they're going to cap out at 6 electrons, right? D's have 5 orbitals, so you're going to cap out at 10 electrons, and F's have 14 electrons, right, for their 7 orbitals. So if you can remember the order, which I'm going to show you guys how to remember the order, it's very easy to actually write an electron configuration. So if we look on the periodic table, and let's write an electron configuration for something a little more involved, like phosphorus. Not a lot more involved, but a little more involved. What I'm going to do is I'm just going to go in order. And phosphorus has 15 electrons, so I have to exhaust my 15 electrons. But I've always got to go in the order here. So I'm going to go 1s2. That's 2 of my 15. I've got 13 left. 2s2. That's 4 of them. I have 11 left. 2p6. So now that's a total of 10. I've only got 5 left. 3s. Right now I'm going in order. So 3s. 3s. 2, so now I've got 12, I only have 3 left. 3p, this 3p could take 6, but I've already used up 6, 7, 8, 9, 10, 11, 12 of my 15. I've only got 3 left, so the remaining 3 just go in the 3p. Right? Hopefully that makes sense. Let's try one that's a little more advanced. Let's do bromine. How many electrons does bromine have? It has 35. All right, so 1s2, 2s2, right? That's 4 of them. I've got 31 left. 2p6, that's 10 of them. We've got 25 left. 3s2, 3p6, right? Well, now, if you look at the order, I have to go to 4s2 next. So 4s2, right? So let's take stock of how many we got. We got 6 and 6 is 12, 13, 14, 15, 16, 17, 18, 19, 20. I still have 15 more to use. Well, 3D, I have more than 10. I can put 10 in the D, in the 3D, right, because it comes next. And then I go to 4P. So now I've used up 10, 6 and 6 is 22, 23, 24, 25, 26, 27, 28, 29, 30. I need 5 more. Well, 4p can hold, any of the p's can hold 6 electrons, so this will hold 5, the remaining 5 just fine. Right? Now, something starts to happen that makes everything a little obnoxious. Because notice, you do the same order every time. 1s2, 2s2, 2p6, 3s2, 3p6. All that really matters is where you stop, right? So if we can just identify where we stop, That's all we really need to do. And I'm going to teach you that trick in a little bit. For now, just work on filling up the order and understanding why this all is the way it is.